Now in this lecture we will see the implementation of few source coding methods and channel coding methods using MATLAB. We will see how we can simulate them with the MATLAB. So first of all we look at the Huffman dictionary. We have seen before how to create this dictionary. I have explained it to you in the lecture of Huffman coding. Now here we will see how we can simulate this implementation of dictionary over here. So first of all we generate a signal, and since in this example I had taken 6 symbols, 1, 2, 6. In this one, I have also taken the 6 symbols. It's not necessary that we should always take this 6 symbols. It can vary. The number of symbols may vary. It can be 3, 5, 8, 10, as many as you like. And then I repeated these symbols 50 times. When I will run the simulation, I will show you what will be the output of this instruction. So the very first thing we have to create this dictionary, what we have to do is that we have to assign probability to each of these symbols, just like we have done over here. So here you can see that in this example, we assume that x1 is 0.4, the probability of occurring x1 is 0.4, 2 is 0.3, x3 is 0.1, x4 is 0.04, x5 is 0.1, and x6 is 0.06. I have taken the same values over here, 0.04, 0.3, 0.1, 0.4, 0.1, and 0.06. So this 0.04 corresponds to 1, 0.3 corresponds to 2, 0.1 corresponds to 3, and so on. Next we will use built-in function of MATLAB, which is Huffman dictionary, and it accepts 2 arguments. It takes 2 arguments. One is symbols, these symbols, and the corresponding probability. I have created 2 vectors over here, symbols vector and probabilities vector, and then I passed these 2 vectors to this function, Huffman dictionary function, which is a built-in function of MATLAB. And once I have created this dictionary over here, I will use this dictionary to code my signal, which is this signal over here. I have taken a very simple signal where I have got 1, 2, 3, 4, 5, 6, all these symbols over here. So let's run this example. So before I continue, I will add up these breakpoints so I can explain you step by step what is happening at each step of this simulation. So you can see that the very first instruction which is executed over here is that we have created a signal which has got symbols 1, 2, 6, and it is repeated 50 times. So as you can see, we have got 6 symbols and we are repeating it 50 times. So we have got altogether a vector of 300 columns. You can see this 1, 2, 3, 4, 5, 6. Then it starts to repeat 1, 2, 3, 4, 5, and 6, and then 1, 2, 3, 4, 5, 6 again. So it will keep repeating 50 times. So this is my row vector. I will encode this signal which I have generated over here. I will encode this signal using Huffman code. Next, I created a row vector of symbols 1 to 6, as I told you, and then another row vector of their corresponding probabilities. As you can see, the number of probabilities and symbols is the same. And it must be, because we have to assign probability to each of these symbols. As we had seen in this one, that the total probability must not exceed 1. This is the condition. So this is the condition. Same condition is over here as well for this Huffman dictionary function to be used. The total probability of all these probabilities of each symbol must be equal to 1. If it will be less than or equal to 1, less than or greater than 1, then this function will not work. It will create error. I will show you what kind of error it will give you. Next, when I will execute this instruction, dictionary, Huffman dictionary, symbols P, so you can see that we have got cells over here. In each cell, you can see that in this column we have got the symbols, and in this column the variable length codes assigned to each symbol. If you compare these symbols with this one over here, then you will see that it is not the same. These symbols are not the same. Our symbols are different. For example, x1 is 1 in our case, but here it is 0, 0, 0, 1, 1, and so on. So it depends how these values are taken by what kind of algorithm is used to create these codes. The concept is the same, the restrictions are the same, the conditions are the same, but it depends because I told you, maybe I don't remember exactly, but maybe I have told you that it depends whether you are taking, if the equal symbols are the same, whether you are going to take the lower one or upper one, or sometimes they take 0 as a path. It depends. There are different ways to create the codes. Anyhow, but one thing is, you can see that they all are prefix-free codes. This is the main condition, if you remember, that we want to create these prefix-free codes. So it should be unique and instantaneously decodable. Second condition was that there must be more than one maximum length code word. So if you look at this code, you have got the maximum length is 2, and we have got 2 such code words. In this one, you will see that we have got a maximum length of 1, 2, 3, 4, 5, and we have got 2 such codes for symbol 1 and for symbol 6. So this condition is also met. Now we will encode the data, and we have used Huffman encode. Encode means encode the data. Encode the data using Huffman encoding method, and I have assigned that to Hcode. You can see that the size of this coded data is 1000. So it is obviously increased. The original data was, the size of the original data was 300 columns, and here I have got 1000 columns, or you may say that here the size of the data was 300 bits, and here I have got 1000 bits data. And that is because of this variable length codes, prefix-free codes. However, in large, as I told you that in large number data, we can reduce the number of bits, but in small size of data, Huffman code is not very suitable or useful. But it is a good example to understand what source coding is and how it works. And there is another method to decode the data, which is called Huffman decoding. And after decoding the data, if you want to see how the decoding data looks like, then we will look at this one. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Again, it is the same. And we will check if it is equal, means the received signal, which is DHSIG, this variable, which is saved in this variable, and our generated data, which is SIG data, if they are equal or not. If they are equal, it means that we have successfully decoded the data. In this example, I have kept it simple, and I have not introduced any error in the data, in the coding and decoding. But in other examples, if we will introduce the error as well. So when this condition is met, where If there is no error, then of course this is equal method will return 1. This is a Boolean function which returns 1 if there is the values in both the vectors or row vectors or column vectors is the same. So it will return 1, otherwise it will return 0. So in this case, as we have not introduced any error, so we know that there is no difference between SIG and DSIG. So this check has returned 1 over here, as you can see. So this condition is true. If check is equal to 1 is true, so we will get the message that the original data and decoded data are the same. So we can use these built-in functions of MATLAB, Huffman Dictionary, Huffman Encode, Huffman Deco to create the dictionary of Huffman codes and encode the data and decode the data. And to check, the simple thing is that we simply compare the received data with the sent data, and if they are the same, they must be same in this case because we have not introduced any error in the simulation. So this check value will be equal to 1 and the original data and decode data are the same. So now I told you that I will create an error. For example, I change this 0.06 to 0.07. Now when I will try to create the dictionary, it will give me error. The error has been generated and it says that the sum of the elements of probability vector must be 1. So it cannot exceed 1. You have got to take care of this when you are creating a simulation using Huffman code, that the total sum of the probabilities must not be greater than 1, not even less than 1. It must be equal to 1. For example, if I make it 0.05, then again it will generate the error. Again, the error has been generated because it must be equal to 1. So we have seen this example, simple example, which is based on our theoretical example, which we had used to understand Huffman coding. Now to use another type of data, it means instead of numbers or symbol 1, 2, 3, we use letters, English letters, to encode the data. Here we have got HELLO, hello, and I have again created this is a cell of arrays. Here I have got symbols and probability of each symbol. Now important thing is that why I have created cell over here, because when we are using letters, then this Huffman dictionary requires the symbols to be as cell. Now the thing is that from where I have got these probabilities, as you will see that it doesn't look like a probability to you because it is 11, 8.4, 7.9, but actually what I have done is that I have divided each element of this row vector by 100. So what actually happens is that this 11.16 becomes 0.11, this 8.496 becomes 0.084. So these are the probabilities of each corresponding letter for E, A, and R. I have used data from Notre Dame University from their website. This is based on the experience, what is the probability of each English letter to be used in a text, how frequently it is used. It depends on the frequency of the letter used in normally English text. Then the rest of the method is the same. So we run this example to see how it is encoded. Again, I add up the breakpoints. So first of all, we have got this cell called signal, and these are the elements of this cell. Then I will create this symbols cell. You can see this symbol cell is created of 26. It is not in the same order as A, B, C, D, E, but all the English letters, alphabets are there. And to each variable, to each symbol, probability is assigned. Next, we again create the dictionary. Now we look at the dictionary over here, and we see that it is a long dictionary, and the maximum size of a symbol is 1, 2, 3, 4, 5, 6, 8. Next, we will encode the data as we have done before. We will encode the data which is HELLO, hello. When we encode it, we see the encoded data. It is in this form over here, H code. If we want to see it in row vector form, we can see that it is graded like this. If you see that what is the probability of H in dictionary, for H we have got 10001. So here we have got 10001 for H. Then for E we have 101. So for E we have got 101. Code for L it is 1100. So it will be appended after that, and this is how the whole data is encoded data is created. Now again we will decode the data, and Huffman, after decoding, what we get over here is that we have got HELLO. We have successfully decoded the data because we have not introduced any error in this example also. So of course, when we check if they are sending data and receiving data are the same, we will get the original data and decoded data are the same message. So this is how we can simulate encoding of data using Huffman coding method and decoding as well. This very simple example. Now we move to Hamming code. First of all, we will see the built-in function of Hamming code, and then we will see use this pattern of parity bits and the method which we had used in our example. So I have used this 7,4 coding of Hamming code. So we can compare it with our lecture as well. It is the basics one also, because we cannot have any encoding less than 7,4, and the reason is that, as we can see, that for Hamming coders R must be greater than or equal to 3. So we cannot have R less than 3. So in this case, the Hamming code requirement is that n must be n should be equal to 2 to the power 3 minus 1, which means that it must be 7. And the requirement for k is that 2 to the power r minus 1 minus r, so it is 4. So it is 7,4. You can see that if r is 3, so we'll have 7,4 encoding method. If we have got r is equal to 4, then we will have 15,11, and for 5 bits of redundancy, we'll have 31,26 Hamming code. So going to encode this data 1010. First of all, we have defined a variable n, which defines the code word length 7, and k, which is the length of the message, and here this is the message which we are going to encode. So as we say that the length of the message is 4 bits, so we have created a data of 4 bits 1010. Then we encode the data using encode method, built-in encode method of MATLAB. And to define this, that it is going to encode the data using Hamming code, we have to write this Hamming/binary within apostrophe. So when this data will be encoded, it will be encoded using Hamming code. And we have to define the data, as well as we have to define the code word length and message length. When this data is encoded, as we can see, this is the data over here. This is the data 1010, and then we encode the data, which is 0011010. This one is different from this one over here, because here we are appending the parity bits at the end of the data. As you can see, these parity bits are added in the message bit. But here it is not using this appending method, or you may say systematic method. It is using non-systematic method. The built-in Hamming code method used by MATLAB is non-systematic Hamming code method. But in this example, we have added the error as well, and we'll see that how this error can be detected and corrected. Important thing is that we know that for 7,4 Hamming code, its capability of detecting and correcting the error is just 1 bit. So it can detect only 1 bit and it can correct only 1 bit. So first of all, I have introduced just 1 bit error. As you can see, insert one error into the encoded data, and that I have error I have created in bit number 3. So if we look at this one after execution, this one encoded data, if you look at this one over here, this encoded data was 00111010, but I have created error at this one, and I have just flipped the bit. This is the symbol of not, means whatever the value is, it will be the opposite of the value. So if it is 1, it will become 0, and if it is 0, it will become 1. In this case over here, it is 1. So if you look at this one, at 3 it has become 0. The rest of the data is the same. Only the bit number 3 has been flipped, and from 1 it has become 0. So I have created error in the data. Now I will decode this data which has got error in it at bit number 3, and I will see whether this Hamming code will be able to detect that error and correct it or not. And what we get over here is that number of errors means there is no error. I use the function bit error, built-in function of MATLAB, which compares the received data and the decoded data. For this decoded data, I have used built-in function decode. As I had used this built-in function encode, I have used this decode. It is only the reverse of encode. Here you have to provide the data which you want to decode, the same n comma k, and defining which kind of coding method you are going to use. So it is Hamming code. Although I have introduced error over here, when I receive the data, I get no error, because if I look at this decoded data over here, and I compare it with my data, it is the same, 1010, and here the data, received data, is also 1010. It means that Hamming code has corrected this error which I had created over here in bit number 3. It detected it and corrected it as well. Now if I make the changes and I insert 2 errors instead of 1 error, I have created 2 errors over here, and the place of the bit errors is 3 and 4. Now when I run this one, what should happen? Again, the rest is the same. This is my encoded data and this is my error data. So if I look at this my encoded data, it is 00111010. I have created error over here, 3 and 4. So my data becomes 3 and 4 have been flipped, so it becomes all zeros except 1. Now when I decode this data which has got 2 errors in it, what will happen? If I look at this decoded data, I find that all the bits are 0. It means that the Hamming code 7,4 Hamming code failed to detect 2 errors and correct them. So what I will get over here is that I receive 2 errors, because here in this send data I have got 1 at 1, bit number 1 is 1 and bit number 3 is also 1, but in this decoded data they both are 0. So it means that there are 2 errors. Hamming code failed to detect and correct 2 errors. Now we look at if we introduce 3 errors. Now I have created error in 3 bits, 3, 4 and 5. This is my encoded data, 3, 4 and 5. So these 2 bits will become 0 and this bit will become 1. So these 2 bits have 0 and this 5th bit has become 1. And when I decode it, I get again 2 errors, because again the same thing happened. It failed to detect and correct the errors. So I have got error in this place 1, here it is 0, Here it is 0, here it is 1. So it has got 2 errors. Now if I introduce 4 errors, instead of 3 errors, I introduce 4 errors, I again receive 2 errors, because this decoded data is all zeros and 1 0 1 0. So you can see that this 4 errors, I have introduced 4 errors. The decoded data is same as when I had 2 errors. So you can see that this Hamming code is not working if it fails to detect and correct the bits. Of course, it cannot correct it until unless it will not detect it. So here it fails to detect and eventually correct the bit, and therefore it will not work for any number of errors greater than 1. Now we will implement 7, 4 Hamming code decoder using the algorithm which we have seen before, where we calculate the parity bits using XOR function by XORing I1, I2, I3, or for parity bit 2, I2, I3, and I4, and then we XOR I1, I2, I4 for parity bit 3. And then we add up these parity bits to the message bit or data bits. So first of all, we XOR data 1 and data 2, which means bit 1 and bit 2, and then we XOR the result with bit number 3, this one. And similarly, we did the same thing for P2 and P3. Then we encoded the data. And how did we encode the data? By simply adding these parity bits to the data. So we can see that our data is 1011, and our encoded data is 1011, and these 3 parity bits are added, because the result of all these parity bits is 0. P1 is 0, P2 is 0, and P3 is also 0. Then insert error. So here I have introduced error in bit number 7. If you look at this data, encoded data with error, I have created error in bit number 7 over here. In encoded data, you can see it is 0. Bit number 7 is 0, but once the error has been introduced, it has become 1. So now we are going to decode the data. For that, first of all, we have to develop the syndrome S. We have to calculate it, and to calculate that syndrome, we have to calculate S1, S2, and S3. And for that, we use this equation over here. This one you can see is very much similar to this one, because here it is called I1, I2, I3, which is the bit of the data bits I1, I2, I3. Here it is representing the same thing, but only we have used notation B because we are using it for receiver. So this is bit 1, bit 2, and bit 3 of the received data, and then we XORed it with bit number 5 of the received data, which is actually the parity bit 1. This is actually P1. So if S1, S2, and S3, all these are 0, it means there is no error. It will show us that S is equal to 0, 0, 0, which means that according to this syndrome table we have over here, if S1, S2, and S3 all are 0, then there is no error. But if there is any error in any one bit, then we will have any combination of 3 bits other than 0. So here, as you can see, this 001 represents that we have got error in bit number 7. So what do we expect that we should get this 001? Because as we have seen that we have introduced error in this bit number 7. So what syndrome should we get? We should get 001. Now let's see if we have got this 001 over here. Look at S, and it is 001. So it means that we have calculated the syndrome successfully. Now what we have to do, we have to find this error bits, error table, this one, according to this 001. So for that, here I have created 2 tables, error pattern and S table. This error pattern is this one. You can see same as this one. All zeros first one, then 001, then 0010. It is the same over here. And this S table is also the same. So this 000 corresponds to this one, first row over here. This second row 001 corresponds to this second row over here, which is all zeros, and 7th bit is 1. So this is actually I have created from exactly the same way I have created over here, this table. Next, what I have to do is that I have to match my calculated syndrome, this S, with whether it matches with which of these values. And I will get this row number and I will find what is the error pattern. So for that, I have used this for loop. This for loop will match this S over here, this one, this S over here, with each and every value in this S table. So first of all, it will compare this value S with first row over here. Of course, it will not match. Then it will match with this one, and it will try this one, and it will compare with all these. So as I know that it's going to match only one of these. So although I could have said that, I mean, once the match has been made, I could have come out of the loop, which will, of course, is more efficient thing to do because we don't have to go through all the table. But for simplicity, I haven't done so, so we can carry on. So what I will get? I should get IDX is equal to 2 because we know that the index of this one is 2. So if I get IDX is equal to 2, then it means I have found the correct index. So if I look at this IDX, as you can see, it is 2. It means that this function has this loop. Through this loop, I have found this row over here, which is same as S. I have used is equal function of built-in function of MATLAB to compare the value. This is the table, and this is the S value, which is being compared by the elements of this table. Now, to get this error pattern, I will just place this index of error pattern because I know this corresponds to this one. So if the error is at row number 2, then the error pattern must be at row number 2. So I have got this error pattern over here, error bit. If you look at this error bit, I execute it. So you will see that it is this one, 0, 0, 0, 0, and 1. So I have got this error bit. Now, once I have got this error bit, this pattern, now I have to see where the error has occurred. To see that, I will find the value of 1 in this error pattern. As you can see that there is only one in each pattern because we have got the only possible error is of 1 bit in 7,4 bit. The maximum error it can detect and correct is 1 bit. So here we have got each one in this pattern is actually representing the location of the error bit. So when I execute this instruction, I have used find built-in function of MATLAB, which will give me the index of the bit. Which, if you can see, bit number is over here is 7. So it will just see where the 1 is from this pattern and will give me the location of that one, which is 7. So what I will do is that I will just correct this bit, and for that I will just XOR the encoded data with error bit, means this pattern. I will XOR them simply. And so this decoded data is, you can see it is 1011. Why I have taken 4 bits? Because we know that the last 3 bits are of the parity. This is systematic decoding, encoding. So we know that last 3 bits were added for the parity, and first 4 bits are for the data. So I have just taken first 4 bits out of this 7 bits encoded received data, and then I simply calculate the number of errors, which is equal to 0. and this is as per our expectation. So we can say that our this simulation has successfully encoded and decoded 1-bit error. Now if I change the number of errors over here, now we have got 2 errors at location bit number 2 and bit number 3. You can see we have got 2 errors because this Hamming code cannot detect more than 1 error. And if you look at this decoded data over here, is 1101, and the actual data was 1011. So we have got error in 2 places over here and here. It should have been 0 and this should have been 1. The data is 1011. Here the Hamming code failed to detect and correct the 2 errors. If I increase the number of errors, say I have got 3 errors, bit number 3, 4 and 5. Here the decoded data is 1000 and encoded data was 10. The actual data was 1011. So we have got error over here and here. 10 is okay, but this 00, we have got 2 errors. Again, it failed to detect and correct the errors. And if we introduce 4 errors, then we have got only 1 error. Because here, this one is okay, this one is okay, this one is error, and this one is okay because our data is 1011. So we have got error over here. So you can see that if the number of error is greater than 1, this Hamming code cannot detect and correct the bits. Now we look at 15,11 Hamming code, and if we use the built-in function of MATLAB, which is encode, and which you have seen over here as well in this one 7,4 before. So first of all, I introduce only 1-bit error over here, and we see there is no error because 15,11 can detect 2 errors and can correct only 1 error. Then introduce 2 errors at location 3 and 7, bit number 3 and bit number 7. Here we have got 1 error because it is capable of detecting 2 errors but correcting only 1 error. So it has successfully corrected 1 bit, but it failed to correct the other error because there are 2 errors in it. So it detected it, but it cannot correct it. Now we introduce 3 errors and we see what happens. When we introduce 3 errors, we can see that the number of errors has increased. It has got 2 errors now. And if we increase from 3 to 4, the number of errors, again it's 2. So we can see that if we have got more than 2 errors, then 15,11 has failed to correct the data. From these simulations, we can see that the capability of each Hamming code and how to simulate it in MATLAB. Thank you.